project on PV integrated multifunctional off-board EV charger with improved grid power quality. Myself, Manjit Reddy. My teammates are Mahesh Reddy, Priyanka Reddy, K. Madhu. Under the esteemed guidance of M. Ramesh, M.Tech, Assistant Professor, Department of EEE. These are the contents of our project: objective, introduction, existing method, drawback, proposed method, advantages, block diagram, applications, software requirements, simulation results, and references. The objective of our project. The main objective of this project is to power the electrical vehicle and improve the power quality by using adaptive not filter based efficient control algorithm. A multi-level topology is adapted for the grid-facing converter to improve output voltage quality. The ANF accurately estimates the fundamental EV current and grid voltage for the generating pure sinusoidal references current and synchronizing voltage template. Introduction. Increasing environmental pollution and limiting petroleum fuels resulted in the two major changes in the world. The first change is adopting renewable energy sources by replacing conventional energy sources, and the second is adopting electrical vehicles by replacing combustion engine based vehicles. The EV batteries are used to mitigate the problems caused by the PV intermittency and utility grid faults, leading to unwanted charging discharging of EV batteries, resulting in reduced battery life. Integrating RES and EV chargers into the power grid creates challenge and opportunities for the system. This is the existing method. In the existing system, sinusoidal signal integrated PLL, positive sequence extractor based enhanced PLL, and SOGA PLL is implemented. However, by using these three methods, there are some drawbacks. The drawbacks are the PLL needs significant improvement in the estimating synchronization reference phase to work effectively under non-ideal grid voltage conditions. Next, PLL, coming to the EPLL, trigonometric calculations impose a high computational burden on the controller and make it expensive during implementation. And again, they have been used SOGA PLL. The transient performance of SOGA at variable frequency leads to serve phase changes. SOGA frequency locked loop is proposed based on the frequency locking instead of conventional phase locking. By adding FFL to SOGA, increases the control complexity and reduces the steady state margin. These are the disadvantages by using the three methods: less power quality, increased in peak load, system losses. Proposed method. In the proposed system, a single excited 7-level cascade H-bridge bidirectional AC-DC converter topology to design the EV charger. An ANF-based unified control algorithm is implemented to maintain the harmonics free grid current with threshold less than 5% and power provide on demand reactive power support to the grid. To maximize the PV utilization, solar PV generation is used for EV charging and simultaneously powering the residential load in both SO and GCO. SO means standalone mode and GCO means grid connected operation. To avoid unwanted charging discharging of EV, and ESS is integrated into the EV charger to achieve improved system reliability during the grid outages and smooth transition from GCO to SO and vice versa. An ANF based phase error minimization technique is implemented for grid synchronization. A multi-level topology is adopted for a grid converter to improve the charger performance during grid synchronization and grid current harmonics. FL is proposed in the based on frequency locking instead of conventional phase locking. An ANF is easy to implement and adaptive to frequency estimation during ideal and non-ideal grid voltage conditions. Block diagram. The proposed charger configuration integrates the grid, solar PV, storage battery, and EV battery to the charging system through grid converter, PV converter, energy storage converter, and EV converter respectively. The power electronic circuitry of the system configuration is presented in the grid converter is a 7-level CH-BDC, also known as Cascade H-bridge bidirectional converter. The converter topology has 3 H-bridge modules as per whose outputs are connected to the primary winding. The proposed charger control algorithm has 4 main objectives. The first objective is it has to maintain the uninterruptible charging of EVs during both the GCO and SO of the charger. The second objective is to enhance the grid power quality in the GCO mode. The third objective is to provide a backup power supply to the residential load during an emergency. The fourth objective is to achieve the smooth, seamless transition between the GCO and SO vice versa. Based on these three objectives, the charger control is developed for GCO S1 green synchronization. Here, the PV powered EV charger supports the three-phase grid by generating continuous power supply to the residential loads and as well as electrical vehicle. When the power is enough to residential loads and the electrical vehicle, the power which is generated by the PV powered EV charger is directly stored to the energy storage system through the energy storage converter. Next, CHVDC control in GCO. The ANF based active component extractor estimates the active component of nonlinear load current. ANF to ACA works in two steps. First, it estimates the fundamental component of nonlinear load current by using ANF, and in the second step, it calculates the active component from the extracted fundamental current. Furthermore, the adaptive nature of the ANF maintains its estimation efficiency irrespective of EV load current distortion and non-ideal grid voltage condition. Next, energy storage BDDC control in GCO. In GCO, the BDDC of the storage battery controls the charging discharging of the solar battery. Constant current and constant voltage. Mode battery charging is adopted. Under CC charging, the reference battery charging current is set to a proper power level until battery voltage touches the rated permitted voltage level. In CV, the battery charging is carried out with constant voltage and decreasing current until the current reaches its rated cutoff level. Next, electrical vehicle BTDC control in GCO. The charging technique adopted for electrical vehicle connected at DC link is the same as the storage battery. However, constant power discharging of EV is adopted here for controlling the EV BDDC. The charger operator, based on the EV owner convenience, decides the discharging power command for EV coupled to DC link. Advantages by using the proposed system is high power quality, less losses in the system, and high reliability. These are the applications, electrical vehicle charging application. These are the software requirements for our project. Software configuration requires operating system Windows 7, 8, 10, and application software requires MATLAB Simulink 2018 version. Hardware configuration, hardware requires Windows OS, RAM minimum requires 8 GB to 4 GB, processor requires i3 and i5 most preferably.
This is the block diagram. So in this block diagram there is the two power supplies. One is solar panel, another one is grid supply. So from this solar panel we are getting the power, and also there is a diode which reduce the unwanted signals, and also there is a rectifier from the grid side also which reduce the unwanted signals. And so from both sides you will get the power supply, and there is a energy storage converter and the EV converter. So energy storage bidirectional inverter is a controllable four quadrant operation converter, so that can convert energy bidirectionally between AC and DC sides. Then here AC power converter can convert alternating current AC into direct current and vice versa. Change the voltage or frequency of the current, or do some combination of this, and the power converter can be as a simple as a transformer, or it can be a far more complex system such as a resonant converter. So here the energy storage converter will storage the power. So at the time any problem in the grid or industrial emergency conditions, so at the time grid will be disconnected from the solar panel power, so the electrical vehicle will be charged, and also the other will be also charged. So these are the simulation waveforms we are getting from the block diagram, from the above block diagram. So this is these both waveforms are the if A phase and B phase grid voltage and EV load current, that is the VGA and VGP and IR and IR. And these two another two waveforms are the A phase and B phase grid voltage VG and VB and grid. And these are the another two waveforms, A phase parameters VGA and IGA and IHR and IR. So this is the dynamic state block diagram. So in this dynamic state block diagram, so at the time there is any problem in the grid or any disconnection from the grid, so the solar panel will provide the power supply to the electrical vehicle. So after operating in the dynamic state, we are getting the block diagrams like this. This is the grid voltage and the grid current, and in so this is the IRR current, I charging current. So this project proposes an ANF based efficient control strategy for grid connected PV powered multifunctional EV charger. To charge the EVs and simultaneously improve the grid power quality, the obtained results verify the ability of the proposed control algorithm. So in grid power quality improvement under all operating conditions, including the non-ideal grid voltage conditions, the charger control always maintains the grid voltage and current THD within the limit set by the IEEE and 5 standard. So the charger operates satisfactory in both CGO GCO grid connected mode and standalone mode. So the proposed ANF based grid synchronization technique maintains a smooth and seamless transition from grid connected mode to standalone mode and vice versa. In the operation, the charger maintains the uninterruptible and EV charging and simultaneously provides a reactive power support and grid current harmonic compensation and backup power supply to the residential load. So the charger optimally draws a power from the PV irrespective of its intermittent nature during all operation conditions. So in grid connected mode, the CHVDC control effectively operates the PV in MPP, and however in standalone mode this is achieved by storage battery converter. So the voltage to grid operation of the EV battery connected to the DC link maximize its system utilization. Moreover, the experimental performance of EV battery chargers shows a stable operation in steady state and dynamic conditions.